Usually we say that something is in a static state when it doesn't evolve or change with time. This means that if we look at the system at a time t1 and at another time t2, we find it in the same state. We can also express this as saying that the system will be invariant under transformations in which t goes to t plus delta t, or using all the coordinates under this kind of infinitesimal transformations. Well, some infinitesimal parameter delta mu 0. If we are talking about a metric, we can say that the metric is static if it has this kind of symmetry or invariance under time translations. In other words, as we know, this means that it has a Killing vector, and the Killing vector has to be time-like, because otherwise the adapted coordinate, which will be this t, cannot be a time coordinate. So for a metric, we are going to demand the existence of a vector satisfying the Killing equation, and also this property that tells us that it is time-like. We know that this implies that there is an adapted coordinate such that k is just partial t, and that together these two equations imply that the metric will be time invariant. When we are talking about time independent metrics, it is useful to write the metric in this form. Okay, this is possible. This form can be used for any metric, not just for a time independent one. See that it is just a rewriting of the components, because if I expand this square here, I find that this is dt squared. Then with a factor of 2, I get dtt omega I dt dxi, and then minus gamma ij minus dtt omega I omega j dxi dxj, and see that we can identify this with the components gti, and this with general components gij. Sorry, with minus, because I have written this minus. So there is no loss of generality in writing the metric in this way. That is just useful for our discussion. If the metric is time independent, then dtt will be independent of time. We are using this adapted coordinate, also omega I, and also this three-dimensional metric gamma ij will be independent of time. Okay, this adapted coordinates, in which t is the time coordinate adapted to the isometry, as we just said, k mu is just delta mu t, and if the metric had this form, k mu is given by g mu t k t, and well, these are these cross terms. This means that this only has has two types of components. So kt is dtt kt, so it's just dtt, and ki is dtt omega I. So if I write this one form in this like this is dt plus omega I dxi. Okay, this more or less what you get here, but without the square. Okay, I have, if you notice, although I started talking about static states of systems, and then I said, well, they have to be time independent, and then I switched it to metrics, and I haven't said that this metric is static, I just said that it is time independent, and that's because a general metric of this form, which is time independent, is not said to be static. A metric of this form, just time independent metric, is said to be a stationary metric. So when do we call a metric static? You have to think on the general situation of this space. You have hypersurfaces, you can of constant time, say t1, and let me draw this a bit further, t2, and so on. And you have a time coordinate which just labels these all these hypersurfaces that foliate the space-time, because you can view your space-time really as divided into these hypersurfaces, which are continually labeled by time. Okay, then you have this vector k mu, and you could say that this vector k mu, which is in principle, well, it is associated to the adapted coordinate t that labels these hypersurfaces, you could think that it is naturally orthogonal to all of them. Okay, it is a vector field, so it is defined everywhere, and it is defined at different points and over different hypersurfaces. And you may think that this is enough. Okay, this construction is already telling you that this k mu is orthogonal to these hypersurfaces. Okay, after all, these hypersurfaces for constant t are space-like hypersurfaces. The normal vector has to be a time-like vector, and k mu is a time-like vector. However, this is not true. The condition for these hypersurfaces of constant time to be normal to k mu is this one. Okay, it has to satisfy this. This condition is called hypersurface orthonormality. Orthogonality. Okay, and it guarantees that if it is satisfied, then this vector, which is the vector tangent to the lines of constant t, is also normal to the hypersurfaces of constant t. This is not at all guaranteed in general. Okay, so you can check that if k mu is given by this general expression, this can only happen if omega I, well, let me put it this way. Omega I j antisymmetrized is equal to 0. This is the condition where we have already used the fact that omega is time independent. So these two things. So what happens when this antisymmetrized derivative is 0? Well, this means that locally omega I is the derivative of some function. You can see that this indeed implies this. You get another derivative antisymmetrized, and since the derivative is commute, you get a 0. Okay, but this is only true locally. Still, our description of the space-time is local. We don't know what the whole manifold is. We never know. We just have a description in some local coordinate patch. So this is enough for us. If omega I is partial I of some f, then you see that omega I dxi, okay, let me put it here. This means that omega I dxi is just d of f, and then you come to the general expression of k mu dx mu, and you see that this is omega, sorry, dt plus df. Okay, if I write it like d of t plus f will be some function of just a space-like coordinates. We don't care very much, but we can always t plus, you can always redefine the time coordinate so that this is called t prime. Okay, if we do that, then the metric takes this form. dt prime squared. So now it is the same function. It was only dependent on spatial coordinates. Then when I change the coordinate t, gdt doesn't change. So as a function, this is just equal to gtt minus gamma ij dxi dxj, and now this is clearly minus gij. So when this vector, Killing vector k, is hypersurface orthogonal, what happens is that, one particular thing that happens is that we can write the metric in this way. So it is block diagonal. For the moment, we cannot say more about gij. It may or may not be diagonal. And the space that satisfies this hypersurface orthogonality, and that which is associated to the fact that omega is given by a partial derivative of some function and so on, and we can write the metric like this, is what we mean by a static metric. Okay, we can say then that static metric is a stationary metric plus hypersurface orthogonality of the time-like Killing vector. This is the rigorous definition of staticity in general relativity. How about spherical symmetry? Well, something is spherically symmetric if it is invariant under the group of three-dimensional rotations, which we know that it is the group S of 3. When is a metric invariant under these rotations? As usual, we are going to characterize this invariance by the invariance under infinitesimal rotations. For each of the infinitesimal rotations, independent infinitesimal rotations, we will have a Killing vector. And well, we know that this group has three infinitesimal generators, which correspond to the infinitesimal rotations in each of the independent three axes. So there will be three Killing vectors that I will call ki. Okay, each of them will be of this form. Okay, and I will take these three values. So I need a variant under the of 3 implies the existence of these three Killing vectors. But how do I know that if I take these three Killing vectors, they really correspond to the infinitesimal generators of rotations? Probably I know, well, I can write rotations in three dimensions in Cartesian coordinates, and then write the infinitesimal generators. I think we did this, and we found that basically, okay, here there is no difference between upper and lower indices. Okay, three dimensions. These infinitesimal generators had this form. Maybe up to a sign, okay, but well, if one is a generator with a different sign, or multiplied by a finite number is also another generator. You can always change basis. This is probably convenient, but okay, we know that these are, for instance, generators in Cartesian coordinates. And in three-dimensional Euclidean space, which is the space with the metric. We put sigma, just to remark that we are not talking about a proper time zone. This is three-dimensional, so this is just delta ij dxi dxj. This is the Euclidean three-dimensional metric. So what happens in higher dimensions? And with other, well, in this case we have also time, and we may not work in Cartesian coordinates because, well, you recognize Cartesian coordinates when you have this metric, but if the metric is different, why should you call these coordinates Cartesian anymore? Well, what we are going to do is not 100% logical. Okay, I'm not saying that this is a proof, but I am going to assume, and there is probably a rigorous proof of the fact that this is the unique way of doing these things. I'm going to assume that I can choose coordinates t, r, theta, and phi in my space-time, where these are coordinates that I call spherical coordinates, even though the metric may not take the typical metric of the sphere. Okay, so let's not get too concerned with that. I just call them like that. Then the other thing I am going to do is to rewrite these vectors in the form that they have in spherical coordinates in Euclidean spacetime. Okay, this form, which is you can find easily. You just have to change coordinates from Cartesian to spherical. It is a simple exercise, so I recommend you to do it. Well, these vectors have this form. This is cos phi. And K3 is just the phi. Well, here you see that phi is the adapted coordinate to K3. Okay, so I think this is the best that one can do, and I am going to show you why. Okay, but I need to discuss first a bit more about Lie brackets. This is just a comment. This is something that I cannot teach you in detail, and that probably will be discussed in the advanced gravity course. If I suppose that I am given these three vectors, but that I don't know that they come from these ones. For these ones, I know very well what is the origin. I know that they generate these rotations and so on, so I know their meaning. But if I am given these three vectors, well, I can imagine that K3 generates rotations around the z-axis, okay, because it generates translations phi to phi plus a constant, and phi is just the angle around the z-axis. Okay, so that much I can imagine, but how about the rest? And why can I say, how can I say that really these three generate the group SO3? They are generators of the group SO3. Well, here comes something that I can't explain in detail, but the idea is that if you compute the Lie brackets of these vectors, well, they are killing in a Euclidean space, but they don't have to be killing yet in a general space. What I'm going to get is exactly this relation, I think, with a minus sign in this particular case. As I have explained, the Lie bracket is something of this kind, given by this. This is the definition. I, so it is antisymmetric and gives you a vector. When you compute this vector, it turns out that it doesn't give you a very strange vector, but it gives you another vector of these three. Okay, which one? Well, the one determined by these coefficients. Now, if you remember what is the Lie algebra of the generators of the SO3 group, you will see that it is exactly the same. And depending on your conventions, there might be a different sign here, okay? Which is not terribly important. But there is a one-to-one correspondence between the commutators. These are 3 by 3 matrices, okay? And this is a commutator of matrices. And it gives you another matrix. Which one? Well, determined by these coefficients, which are the structure constants of the group SO3, and that characterize infinitesimally what the group SO3 is like around the neutral element 0. So you see there is a one-to-one correspondence with these vectors. The only difference is that instead of being a commutator, what you get here, you have here, is the Lie bracket. So, well, what characterizes the symmetry groups infinitesimally is this set of Lie brackets, and well, the set of all these the Lie brackets. Well, let me put it the other way: the space, the vector space generated by these vectors and equipped with this Lie bracket is what is called a Lie algebra. You probably have heard about Lie algebras in the context of matrices. They are very much used in particle physics, but there is exactly a one-to-one correspondence with algebras of vector fields with Lie brackets. And they are very much the same, and of course there is a geometrical explanation for all this. Remember the definition of Lie group that I gave you at some point. They are spaces, so they have spaces in which each element is an element of each point of this space is an element of the group. So there are vector fields on those spaces and so on. Okay, so this is not so strange that there are these Lie algebras of vectors. Now the next thing that I'm going to do is to assume that the metric that we are going to deal with, which is spherically symmetric, is a metric that admits these vectors ki as Killing vectors. So spherically symmetric well is one that satisfies this condition. These three conditions for a equal 1, 2, 3, and given by the vectors above, because I know that these vectors generate the infinitesimal transformations of the infinitesimal rotations of SO3. So this is my definition, and if you don't see the metric, you have to look closer because the metric is here in the connection. So if I know what the Killing vectors are, and I know them in these coordinates, okay, so this is assuming that your metric is written in terms of the coordinates t, r, theta, phi, okay, so these two are invariant under these transformations, which only act on theta and phi. Then you say that this metric is spherically symmetric if these three vectors are Killing vectors of the metric. Okay, so this is a constraint on the metric, and we are going to exploit it. And now that we are at it, well, what happens if we say that it is also static? Okay, then we say that there is an extra Killing vector, now without indices, okay, and that this Killing vector is just this one, again, for this coordinate. So this Killing vector tells you that the metric will be invariant under shifts of the coordinate t. If t is the way we have written this, t is already the adapted coordinate, and we are saying that the metric is time independent. And now you could say, okay, but I know that phi is the coordinate adapted to rotations around the z-axis. And now you are telling me that you are using another adapted coordinate, but you gave me a theorem that was saying that I can only use coordinates adapted to two Killing vectors if they commute. So indeed, okay, I have to impose that this Killing vector has vanishing brackets with the other three. Not just with the one with phi, because otherwise there would be some privileged direction. Okay, the z-axis would not be equal to the rest, and really you want spherical symmetry. You really want that the three vectors, so rotations around the three axes, have the same properties. In this case, that they have vanishing brackets with the generator of time translations. So this is what a static spherically symmetric metric is. It has four Killing vectors, one of them that we call k, and it generates time translations. Another three, which we have chosen to parameterize in terms of theta and phi in this way, and which satisfy this Lie algebra. And well, these four vectors, these three, have vanishing brackets with this k, okay, and that's it. This is spherically symmetric and static. Okay, and I have told you, I don't know how many times, that this is very useful to simplify the form of the metric, and then this means a simplification of the Einstein equation. So let's see exactly how this works. I am going to do this in detail, so it could be the calculation is a bit boring if you want, but it is just gives you some practice. Okay, let us focus. Okay, the metric, just because of the existence of these two conditions, I know, I just proved it before, that I can rewrite the metric in this form: dt dt squared plus gij dxi dxj. This is what I called before minus gamma ij. This gamma ij is definitely positive and gij is definitely negative with my conventions. This gtt is and gij are all time independent. Now let me focus on only this part, okay? And let me expand it. Using the fact that the coordinates 1, 2, 3 are r, theta, and phi. So this is just dr squared plus, these are off diagonal components, theta dr d theta plus 2 times dr phi dr d phi, then d theta theta d theta squared plus 2 times d theta phi d theta d phi plus g phi phi d phi squared. And now let us impose these three equations here. Okay, the way in which these equations are written in the notes are LKI G mu nu. So this is 2 times. Okay, it's not just that it is a shorthand, it's that this operator is very important. It represents the action of this vector field on the metric, but also on other fields if you want. This operator is called the Lie derivative, and you will know more about it in the advanced course. Okay, and now what I really want to do is to expand this in the way in which we originally obtained this equation, which is ki rho partial rho g mu nu plus partial mu ki rho g rho mu plus partial mu ki rho g rho mu. This is the form that these equations have. So let's start with K3. Okay, remember that K3 is just dd phi or partial phi. It is the adapted coordinate to this isometry. It's an isometry because we have assumed that it is, because the metric is spherically symmetric. Now let's go to this equation. You see that the first term will be partial phi g mu nu, but that this the second and the third term contain partial derivatives of the components of K3, but the components of the K3 are delta mu and phi only, these constant components. Okay, so this plus 0 and plus 0, and this is equal to 0. And what you get from this is, well, something that you should have known from the beginning, which are that all the components are not just time independent but also phi independent. This certainly simplifies our equations, but still we haven't been able to eliminate any of the components, which is probably what we would like to do. Now let us consider what happens with the Killing vectors k1 and k2. What we want to impose are these two conditions, but we want to do it component by component. We will start with GRR, which is the first one in this expansion that we have made. Let me start with just K1. Okay, of course I need also to consider GTT, but let's first consider GRR. And according to the general formula, okay, and using the fact that K1 and K2 only have spatial components, I already write just I here. Okay, this is GRR plus partial R K1 I GIR, and the interchange between these two indices, so in this case it's just a factor of 2. But K1 and K2 are both independent of R, so this term vanishes. And so this would be the same if I consider 2. It is really not so different. And GRR, as the rest of the components of the metric, is phi independent, which means that only the component theta will be relevant. Here, this is equal to 0, and it doesn't matter if it is K1 or K2, the conclusion is that GRR is independent of theta. If I had considered the component TT, well, this would be the same, okay, but with R replaced by T. K1 and K2 are time independent, and here I would have GTT, and the conclusion would be entirely analogous, that GTT is also theta independent. Okay, this is the immediate conclusion. And now if you add the fact that they are also phi independent and T independent, the only dependence that GRR and GTT can have is R dependent. So GTT is GTT of R and GRR is GRR of R. Okay. Now let's move to the next component, because we have analyzed GRR under the four Killing vectors. The next component would be GR theta, and let's start with K1. Okay, I will already use from the beginning that GR theta is phi independent, so the only thing that matters here is this component, so the derivative with respect to theta. Then we have partial r K1 I G I theta, but this is r independent, plus partial theta K1 I G R I. Okay, these are the two possibilities. And just substitute the value of the components of K1 theta. They are given up here. It is minus sine theta so this is minus sine phi d theta gr theta, and here we have two possibilities: partial theta K1 theta gr theta plus partial theta K1 phi gr phi. Actually, since I could, we just have here this component K1 theta, and we know that it is theta independent, so this part of the equation disappears. And about K1 phi, okay, this is it's up here, it's just minus cosine theta divided by sine theta cos phi. So it's going to be minus cosine theta divided by sine theta and cosine phi gr phi. Now the derivative with respect to theta gives me 1 over sine square theta. Cosine phi is untouched, and this is the r phi, and this is equal to 0. This is one equation that I get that relates the r theta and the r phi. Well, if I do the same with respect to the Killing vector K2, also of the same component, I can already save several steps because I get exactly the same, up to the fact that instead of minus sine phi, I get I think cosine phi, and here sine phi, but the rest is the same. So I will get plus cosine phi d theta gr theta plus 1 over sine square theta, and instead of cosine phi, minus sine phi, so this is minus sine phi gr phi equal to 0. This is another equation involving the same variables, but then it's obvious that if I multiply this first equation by cosine phi, and this one by sine phi, I can get rid of the derivatives, and I get something, okay, which would be cosine square phi plus minus sine square phi, but I don't care very much, something finite times gr phi equal to 0, from which I conclude that the component gr phi is equal to 0. But if gr phi is equal to 0, then d theta gr phi theta is 0. So these are the two conclusions that I derive. And now you see that, well, all this effort is paying off, because we have already shown that one of the components is 0. Okay, to perform similar calculations involving dr phi. This I'm not going to do because it is just the same. And using the fact that dr phi is already 0, you have proven this, you are going to arrive to the conclusion similar to this calculation, that gr theta is not just independent of theta, but it is identically 0. Okay, and then let's come here. We have to deal with this. This we have shown that is 0, and we have shown that this is 0. So now let's go to the component g theta theta. We compute the derivative with respect to k1, and taking into account the fact that g theta theta is phi independent, we only get a derivative with respect to theta. Really, this calculation is very similar to the calculations that we have done here. We are going to get the theta k1 I g I theta, and because this time is diagonal, to get a factor of 2. And now remember that k1 is minus sine phi k1 theta. This means that it is theta independent, so if I come here, the only possible component is only one that will give an unvanishing contribution will be phi. So this is what we get, theta theta, and okay, this calculation we have already done. It gives us sine squared theta cosine phi g phi theta equals 0. And if we do the calculation with respect to the same calculation but using k2, we are going to get a similar equation, but with sine phi and minus cosine phi interchanged. And then we proceed as before. We multiply the first equation by cosine phi, the second by sine phi. The derivative of theta with respect to g phi vanishes, and the conclusion is that g phi theta is 0. But then if g phi theta is 0, you plug this back into any of these two equations, and you find that g theta theta is theta independent. It's also a function of r only. Let me write this explicitly. Okay, let me come back here where we had all the list of the components. So this one vanishes as well. We prove that this is only a function of r, and this is only a function of r. So it only remains to study g phi phi. Let us take the derivative with respect to k1, and as usual, you know that this is only k1 theta, because g phi phi is also phi independent, and because this is also diagonal, we get a factor of 2, and k1 I g I phi. Now take into account that only g phi theta is 0, g r theta, g r phi is also 0, so the only possibility is that k1 phi contributes here, so we have an equation on phi. Then we substitute the values of the components of k1. This was minus sine phi, then the theta g phi phi, plus, and okay, there's this factor of 2, then we had minus cosine theta sine theta, and there was cosine phi, but the derivative is minus sine phi, so we have sine phi, and the minus disappears, and then g phi phi. There is an overall factor of sine phi here, so eliminating it, we just get phi phi plus 2 times cosine theta sine theta g phi phi equal to 0. Okay, and this is the equation that we have to solve. If you want, for instance, to, well, actually this equation can be integrated if you do the following. You multiply the whole equation by 1 over sine squared of theta. If you want, let's with an extra minus sign, because then you realize that what you have here, which is plus 2 cosine theta sine cube theta, all this is actually just the partial derivative with respect to theta of 1 over sine squared theta, and the whole equation then becomes partial theta g phi phi divided by sine squared theta equals 0, okay, which tells you that g phi phi is sine squared theta times a function of only r, because it cannot depend on phi, it cannot depend on theta. So this is what you get. If you consider now the derivative with respect to k2, you get exactly the same result, so nothing new. Now it may seem to you that we are finished because, well, when you look at this table, we have considered the derivatives of most components. Okay, we have concluded here, we have treated this, and we have shown that g theta phi vanishes. We haven't considered the least derivative of g theta phi, probably because g theta phi vanishes, but this is a common error. The fact that this component vanishes doesn't mean that the component of the equation vanishes. Okay, so we'll see that this has to be considered. Really, what we want to say is that this is the theta phi component of what you get by acting with this least derivative on g. Okay, we write g theta phi because, well, we are lazy people, but this is why you make mistakes sometimes. Let me show you that this equation is non-trivial even when I use the fact that g theta phi is 0. So this will be k1i partial I g theta phi. Indeed, this is 0 plus partial theta k1i g I phi, but this doesn't have to be 0. Okay, if theta phi is 0, then what I know is that this will be phi. And then I have another component, g phi k1i d I theta, but in principle this could be just theta. Okay, I'm just using the fact that all the off-diagonal components vanish. Now let's see if these derivatives are different from 0 or not. I know that they are not vanishing. This d theta phi gives me 1 over sine squared theta cosine phi g phi phi. And this one, I know that this component is minus sine phi, so it gives me minus cosine phi g theta theta, and this equal to 0. Okay, so up to an overall factor of cosine theta, what I get is that g phi phi divided by sine squared theta, which is precisely the thing which is theta independent, is g theta theta. Or a better way of writing this would be g theta theta. Okay, and if I do the same with respect to K2, I am going to get the same. Okay, the same, exactly the same equation. So, summarizing the results, now I come back to this general expression of the metric, and I know that the static spherically symmetric metric is characterized by these components, dtt of r plus grr of r dr squared plus g theta theta, and now the way to write this more easily would be d theta squared plus sine squared theta d phi squared. Okay, I am using the fact that d phi phi is just sine squared d theta theta, and this is just a function of r. And this is what we have always written as d squared of omega. But observe that we have not started with this form. We just assumed that there were some coordinates and that these vectors acted on the metric in a nice way, and they satisfy this algebra, so this is sub 3, and we have imposed that these vectors are Killing vectors. And the consequence is that all the metrics which satisfy these staticity and spherical symmetry properties can be written in exactly this form, which is a result really nice and powerful. This is much easier. You only have to deal with unknowns, 3 unknowns in principle, which are functions of r. So let us make some comments on this. First, about the meaning of the coordinate r. In the Euclidean metric, when we write it in spherical coordinates, r is the radial coordinate. It tells you what is the distance from the origin to the point under consideration. This is no longer true here. It is called, usually it is called radial coordinate because, well, what else would you call it? But it doesn't mean that it is the distance from a center of symmetry to some point. This is not true, and you will see exactly how it works. Okay, and we have to still to use some freedom in the parameterization of R. Okay, that we can use to simplify even further this metric. And when we do it, we will discuss precisely this the form of the metric. Okay, I have written, sorry, this square omega. I mean. Okay, this is one. This is one of the comments. The other comment is this: suppose that I want to know what the existence of Killing vectors means for the curvature, or in particular for the Ricci tensor, which it is also a symmetric covariant rank 2 tensor. Symmetric covariant rank 2 tensor, just like the metric. What can I say about the existence of Killing vectors? Well, this Lie derivative that tells you that something is invariant under the action of these vectors has exactly the same form. You just replace g mu nu by r mu nu. But does it have to be 0? The fact that g mu nu, so let me ask, if you have this property, does it imply this? Well, I can really prove this by saying that I can always choose some the adapted coordinate to the coordinate adapted to k. I can always use the coordinate adapted to k. Let's suppose that it is t or c. Okay, so in these coordinates, what they have is this property. But in these coordinates, this means that since the the connection is just a function of g, so the connection will also be independent of this coordinate, and also the same is true for the Riemann tensor. But this is also true for r mu nu. But this then this equation in this adapted coordinate is exactly equivalent to this, because this is exactly what happens for the metric. So yes, okay. And this means that all the results that we have obtained are also true for r mu nu. This means that one r mu nu will be diagonal in these coordinates. Secondly, that r tt, r, and r theta theta are only functions of r. And third, that r phi phi will be given by sine square theta r theta theta. This means that in principle I don't need to compute r phi phi because it is given by r theta theta. If this also means that by consistency, since g phi phi is also sine squared theta g theta theta, then g phi phi is equal to sine squared theta g theta theta. Then by consistency I can only find solutions if t phi phi is equal also to sine squared theta d theta theta, but it doesn't make sense to have a spherically symmetric gravitational field if the matter distribution is not spherically symmetric, and matter distribution is also given by some t mu nu. You expect similar conditions for t mu nu. The fact that they are the components are only the diagonal, those are the only ones which are non-vanishing, that they are functions of r, and that t phi phi and t theta theta are related by this equation. Now let's go back to the issue of the meaning of the coordinate r. What you know is that if you want to find the area of some two spheres of constant, so for constant t and constant r, okay, well, constant t doesn't really matter here. You have these are what kind of surfaces are these? Okay, I can look at the induced metric when t is constant. dt squared vanishes. When r is constant, dr squared vanishes, and the only thing that we get is g theta theta r d theta squared plus sine squared theta d phi. But this is a constant, okay? And this is the metric of a two-sphere of radius 1. So you can see that this is the metric of a two-sphere of radius square root of g theta theta. Sorry, there is no minus. This is already negative. Minus g theta theta of r. Or in other words, it makes sense to call this g theta theta minus r squared of r, and this r, capital R, really has the meaning of the radius of the sphere given by the parameter r. So r doesn't have the usual meaning that you expect. Okay, if you compute the area of these surfaces, or which is the volume of these two-dimensional surfaces, this you will find it is 4 pi r squared r. This is the standard meaning. Okay, now let's see if we can we can redefine r. Since it doesn't have a very particular meaning, we can get rid of it or use it, let's say, we can reparameterize r by another r and still keep this form of the metric. The functions will be the functions GTT, ER, will be functions of the new R, but we may use this to get rid of some of the components. This can be, you can do this in several ways. Okay, let's go this way, A. Okay, let me write the metric first in this form. R squared minus R squared, the omega squared. What we want to do here is to have something similar what you have in Euclidean space. In Euclidean space, you have dr squared plus d plus r squared, small r squared, the omega squared. Okay, we want to have something like this times some function here. How can we bring the metric to this form? Well, I would perform a change of the coordinate r to some r prime. Okay, and I know that what I get is I remove this dependence, dr prime squared dr prime squared, and here I just replace this by r prime. And now what I want to do to have is that this factor, sorry, this is a plus, drr is negative. This factor is equal to this factor, so times r prime squared. So dr prime squared. So let me do it. It's more detail. I want to have here I prime squared. I want to leave this, so I divide this by r prime squared, and then what I really want is to have this r squared divided by r prime squared. If this is satisfied, then I can write this with a common factor like this, which is what I really wanted from the beginning. Okay, this is one way of getting rid of one independent function. Then I will have one and another one here. Okay, solving this differential equation is more or less trivial, because you know dr, you know r squared, this is r prime squared, then this is a differential equation which is easy to solve depending on the complexity of the functions that you get. But well, you will get an integral immediately, and the integral may be difficult to solve, but you get this form. Then we call this function that you get here h squared. So in this form that I call A, the metric has this expression. Sorry, let's call it minus h squared. The r squared plus r squared the omega squared, because I don't want to write primes. So once I have done this change of coordinates, I replace r prime by r again. Okay, I'm not dealing with a particular metric, so this is just to tell you that the metric can be written in this form, and then I only have these two independent functions. This is typically done to rewrite this as the x squared, the Euclidean metric, and in this case, you, instead of functions of r, you probably want to write this as a function of x. At this moment, I cannot tell you why you would like to do this, but this is one of the uses. If you don't want to write this as dx squared, you can just leave it like this, but you only have two independent functions. The second possibility is that you want to define really a new, we have called it a radial coordinate, because it's just easy to call it like that, which has the meaning that the spheres of radius that particular r have area 4 pi r squared. So we want to call this r squared of r prime squared. This defines the new coordinate for you. Then if you do this, and then again you replace r prime by r, because you don't want to write everything in terms of prime coordinates, your metric takes this form that we can call B. Then plus GRR of r dr squared minus r squared. And this is directly the coordinate, not a function of the coordinate. And the meaning is, as we have said, that the area of the surfaces of constant t and constant r is just 4 pi r squared. Okay, we will use this form of the metric, but we will call GTT lambda because it is shorter, and DRR we'll call it 1 over mu. So the metric in this form will be lambda of r dr squared minus dr squared divided by mu of r minus r squared d omega squared. Okay, and this is much simpler than the original metric, of course. And finally, the other thing that we can do is to impose the condition that GRR is the inverse of GTT. Okay, so these two components are related in this way. And I'm going to call this GTT also lambda, and the metric takes this form. Lambda minus the r squared over lambda, and the one that we call r squared of r d omega squared. Okay, we will compute the Christoffel components and the components of the Ricci tensor maybe in another video, just as an exercise. They are given in the lecture notes for your use, but what you should try to do, first of all, you should try to compute them, okay, just to get practice. And at the very least, you should try to check that the property that we derived for the Levi-Civita connection is satisfied. So you compute the determinant of the metric, take the absolute value, take the square root, the logarithm, and take the derivative, and you should get exactly what you get by contracting all these components. You should also, well, you will see that the components of the Ricci tensor indeed satisfy the property that we advanced. Now the discussion is which of these forms of the metric is more convenient or better. Well, it depends a bit on the problem that you are considering. Sometimes one is better than the other. Sometimes the difference is not easy to see, and knowing this beforehand is just complicated. Okay. Sometimes there is no easy way to see which of these two forms in particular is better to solve a given problem. The next thing that we are going to do is to solve the vacuum equations for a static spherically symmetric metric to find the Schwarzschild solution. We will use in particular this form because the equations turn out to be a bit easier to solve.